Hey everyone, welcome. Today we're going to build a toolkit, a chemist's toolkit actually. We're going to tackle something called stoichiometry. Now I know, sounds like a big scary word, but really it's just about figuring out the amounts of stuff in chemical reactions. Simple as that. So, you ready? Let's jump right in.
Have you ever followed a recipe? Like, for real? Because chemistry is a lot like that. It has its own recipes. You know, when you're baking a cake, you need just the right amount of flour, sugar, eggs. If you mess up one ingredient, the whole thing can be a disaster, right? Well, chemistry it's pretty much the same deal. And today, we're going to unlock the rules that govern those chemical recipes.
Okay, so where do we even start? Well, it all comes down to one golden rule. Seriously, this is the fundamental, unbreakable law that all of chemistry is built on. Get this, and you've got the foundation for everything else. And here it is, the law of conservation of mass. All it means is that matter can't be created or destroyed in a chemical reaction. You can't just, poof, make atoms appear out of nowhere. And they can't just disappear either. Whatever you start with, we call those the reactants, has to weigh the exact same as what you end up with, the products. What goes in must come out.
And that right there, that's the whole reason we even do stoichiometry. It's the why behind all the math. Because if every atom that starts a reaction has to be there at the end, well, we need a way to track them. It's like we have to be super careful accountants for atoms, making sure the books are always balanced.
So, let's see this law in action. Look at the equation on the left, the unbalanced one. Honestly, it's kind of lying to us. It makes it look like an oxygen atom just vanished. Poof, gone. But that can't happen, right? So, look at the after column on the right. Once we balance it, it all makes sense. We start with 4 hydrogens and 2 oxygens, and guess what? We end with 4 hydrogens and 2 oxygens. See? The books are balanced. Every atom is accounted for.
Okay, so we know we have to follow this golden rule. But how? How do we actually do it? Well, that brings us to the next tool in our toolkit. This is how we do that atom accounting we were just talking about.
It's all about balancing equations. And what that means is we're just adjusting these big numbers in front of the molecules. We call them coefficients. This part is so important. We're changing how many molecules there are, not what the molecules are. Big difference.
Let's walk through an example. Look at this reaction for burning propane. There's a method to the madness here. You just go one element at a time. First, you balance the carbons. See that? We put a 3 in front of the CO2. Then, you balance the hydrogens, so we pop a 4 in front of the H2O. Now, here's a pro tip. Always save elements that are by themselves, like that O2, for last. It's way easier. You just count up all the oxygens on the right. Let's see, that's 6 plus 4, so 10 total. And then you can easily balance the O2 on the left by putting a 5 in front of it. Boom, balanced.
Okay, listen up, because this is probably the single most important rule of balancing equations. You can change the big numbers, the coefficients, all day long. But you never, ever touch the little numbers, the subscripts. Why? Because if you do that, you're not just tweaking the recipe anymore, you're changing the ingredients entirely. Think about it. H2O is water. You drink it. Change that little subscript and you could get H2O2, which is hydrogen peroxide. You do not drink that. Big, big difference.
All right, so now our recipe is perfectly balanced on paper. But what happens in the real world? What if you're in the lab and you run out of one ingredient before the other? I mean, you're not always going to have the exact perfect amounts, right? So what happens then?
This is a super common problem, and it brings us to the third tool for our kit, figuring out which ingredient is going to run out first and grind the whole production line to a halt.
You know what? Before we get back to the chemicals, let's just think about making sandwiches. Imagine you have 10 slices of bread, but only 3 slices of cheese. The recipe is simple. 2 slices of bread, 1 slice of cheese. How many sandwiches can you make? Well, only 3, right? Because after the 3rd sandwich, you're out of cheese. Doesn't matter that you have all that extra bread left over, the cheese is what limited how many sandwiches you could make. It's your limiting reactant.
And that's literally all a limiting reactant is in chemistry. It's the cheese in our chemical sandwich. It's the one ingredient that gets all used up first, and it's the one that decides the absolute maximum amount of product you can make. Anything you have left over, we just say that's in excess.
Okay, let's apply that to a real reaction. We're making water. Let's say we start with 5 moles of hydrogen and 2 moles of oxygen. Now, our balanced recipe says we need 2 hydrogens for every 1 oxygen. So, to use up all 2 moles of our oxygen, how much hydrogen would we need? We'd need 4 moles, right? A 2-to-1 ratio. Well, look at what we have. We've got 5 moles of hydrogen. That's more than enough. So we're going to run out of oxygen first. That makes oxygen our limiting reactant. Simple as that.
So, let's recap where we are. We have a perfectly balanced recipe. We even know which ingredient is going to run out first. We're all set, right? Well, not quite, because in the real world, things rarely, if ever, go 100% perfectly. And that brings us to the last but super important tool in our stoichiometry toolkit. And that tool is called percent yield. You can think of this as, well, it's like the grade you give your experiment. The theoretical yield is your 100%, your A+. It's the absolute max amount of stuff you could possibly make in our perfect world, based on your limiting reactant. But the actual yield is what you really got. It's what you actually weighed on the scale in the lab. So the percent yield just tells you how well you did. How close did you get to that perfect score? So, let's say your math told you that you should have gotten a perfect 10 grams of product. But then you go into the lab, you do the reaction, you weigh your final stuff, and you only got 7 grams. You plug those numbers into the formula, and you get this, 70%. Okay, so it's not 100. What does that actually mean?
It means your reaction was 70% efficient. You did pretty well. You managed to make and collect 70% of the maximum possible product. But what about that other 30%? Well, it got lost somewhere. Maybe some unwanted side reactions happened. Maybe you spilled a tiny bit transferring it from one beaker to another. Or maybe the reaction just didn't feel like going all the way to completion. It happens. That's reality.
And there you have it. That's the whole toolkit, right there. Think about the journey we just took. It all started with that one golden rule, the law of mass conservation. That law told us we had to balance our equations. Once we had a balanced equation, we could figure out our limiting reactant. And knowing that allowed us to compare our theoretical best-case scenario with our actual results using percent yield. See how it all connects? It's a perfect, logical flow from a basic law to real-world results.
So that leaves us with one final big question. We figured out how to write the perfect chemical recipe. But what happens when a reaction just decides not to follow it perfectly? What makes some reactions fast and others slow? Why do some stop halfway? That's the door stoichiometry opens for us. It leads us to even cooler topics like kinetics and equilibrium. But that is a story for another day. Thanks for sticking with me.